is the rounding one. So we talk about it, if a number is given to you, for example, if you have something like 1.49, and if you want to round that to the 10th place, so if it's going to be rounded, if you want to round that to the tenths, rounded to the tenths. So in that case, what is going to be the one? So you have the 1. This is your 1.49. So we locate the rounding digits, which is going to be 4. Then since you have the 9 here, usually added 1 unit to the 1.49, so that's going to be 1.5. So that gives you 1.5 when you round it to the round it to the 10th place. But this is not going to be the only number that would be rounded to 1.5. So for example, if you have something like 1.48, and if you round that gives you 1.5 again. If you have 1.47, if you round that gives you 1.5. So there are going to be many numbers over here that if you round that, you get approximately 1.5 over here. So you can do it the other way around. The other way around is if you have 1.51. If you round it to the 10th place, you see if you round it to the 10th place, that gives you 1.5 again. If you have a 1.52, if you round it, that gives you 1.5 again. So there are going to be an interval of the numbers, if you like, that take you to the 1.5. So I told you the other night that when we say rounding to the 10th place, so this 10th place means when you round, you may lose something or you may gain something. Look at this one. 1.49, you get 1.5. So you gain something. You see, in these cases, you gain something to get it to 1.5. But when we get to the 1.51, 1.52, you lose something. So this 1/10 is going to be kind of, we call it percentage of error. How much are you going to prepare, you prepare to lose or to gain, if you like. So if you put it on the number line, you see this is going to be the number line. And this is going to be the point of 1.5 that we talk about it. This is 1.5. So when we say you round it to the 10th place, so this means you can go to the right or to the left, but the difference between these estimation must be at most 1/10. You see you have the 1/10, 1/10. 1/10 is going to be the same as this is it's going to be 0.1. So the reason that you do this type of operation is it's like if you divide 0.1 by 2. If you divide 0.1 by 2, that gives you something like 1/20. And if you multiply by 5, that gives you 0.05. So the thing that you did is, this is a 1.5. If you go to the left and you go to the right as much as 0.05, so look at this one. You go from this side, this is 1.5. If you add, what's that? It's going to be 0.05. So that gives what? That gives 1.55. So from 1.5, if you go to the 1.55, over here, and if you subtract it, you see this is 1.5, that's a plus, minus what? 0.05. If you subtract it, that gives you the case. So this means if you pick the number, you see if you get this interval from 1.5, if you start from 1.45 and you go to the 1.55, any number would be rounded to the 1.5. You see, any number to the right or to the left. So you start with the 1.5. You see this is going to be 1.45. And on the other side, we get 1.55. So any number in this interval, if you pick any numbers in this interval, that number would be rounded to the 1.5. That's the meaning of rounding. If you understand this one, then you understand calculus. You see the way you do it in everyday life, you just think about that, that decimal points. You just, increasing 1 unit or forgetting about that. But that's the procedure of the rounding. So when you round, you estimate the number. You estimate the number. When you estimate, you lose something or you may gain something. So the tenth means your tolerance. So when you say rounded to the 10th place, this is it. This is 1.5. You go to the left or to the right as much as 0.05. Any number in this interval would be rounded into the 1.5. Okay, so that's the meaning of the rounding of the number in everyday life. Any question? Now, how about limit of the function? When we talk about the limit of the function, remember the function. What's the function? Function is y equal to the f of x. If you want to find the value of the function, the exact value, you drop the numbers in it. Okay, you find f of 2, f of 3, f of 4. So what we would like to do is, we would like to do the same procedure. We would like to estimate the value of the function around the given one. This procedure would be called the limit of the function that I'm going to explain it for you, okay? You get these numbers. What is this one? No. You see for the 1.55, I put the parentheses. The parentheses means you cannot consider 1.55. Okay, you see, 1.45 is included, but 1.55 is excluded. This is it, excluded. Because yes, you are right. If you pick 1.55, that is 1.6. Okay, so this is going to be the case. Now, let's see what we did. So what we are going to do is, you see, we are going to give a notation to tell us when you estimate it from the left or to the right. So let's go with this notation first. This is very important notation for us. Notation, again, this is it. The notation is going to be, suppose a number is given to you. Suppose A is a given number. Okay, suppose A is a given number. Then I want to estimate. Then we are going to say, we say X approaches. This is the expression that we're going to repeat over and over. Okay, X approaches, okay, or sometimes tends, okay, tends to, approaches the number A, okay, the number A from, okay, from the left, okay, if X is less than A, but X is close to A, okay? If X is going to be, okay, F is less than A, but X is going to be, okay, very much close to A. It's going to be close to A. So this means X can take any values. Okay, X can take any values. You see, this is the situation I'm going to have. This is the number line, and this is A. If you're coming from these sides, you see, coming from these sides, so this means you're taking any value. So this is going to be your X. If your X getting closer and closer to the A from the left. In this case, we write X goes to A, but from the left. From the left means x goes to a negative. Okay, so if you see this notation, x goes to a negative means x is approximately equal to the a, but x is less than a that we're going to have. We got this one. This is 1.5. If you pick any number over here, you see between 1.45, any number. All these numbers are going to be what? All of them are less than 1.5. All of them are less than 1.5, but eventually they rounded up to the 1.5. So this is going to be getting closer and closer to the a, but from the left. Any question? So x goes to a, again, means x is less than a. X is less than a, and x is approximately a, if you like, close to a. That's a case one. Question? The other way around, the other direction. Similarly, again, we write x goes to a positive. A positive means this is going to be a positive. This is a. You want to estimate, but you're coming from these sides. This is going to be your x. Again, you saw it here. You see this is 1.5. There are many, many numbers to the right that eventually it round up to the 1.5. But these numbers are, okay, this is it, 1.51, 1.52, etc. So from this direction, we write x goes to a positive, okay, when x is going to be greater than a, and x is approximately a. Okay, so this is going to be, okay, the case. So when we write a positive from the bigger values, a negative from the smaller values. Question? Now, therefore, we have another one. So the last one is going to be also, we write, okay, we write x goes to a. What does it mean? This means x is approximately equal to the a, but x can be less than a or x can be bigger than a. So this is going to be the case if and only if x goes to a negative and x goes to a positive. So this is going to be the case. This is the number a. We don't care about the a. That's why I make a hole here. So this means going to rows the a from the left or going through the a from the right. Okay. So basically, x goes to a means this means x is not equal to the a, but x is close to a, but x is going to be close to a. This notation makes things very easy for us, to continue. You see, the notion of the limit is very important. It's foundation of mathematics, but we are not math measure. Okay, so that's what we would like to do. Would like to give you somehow a very mild interpretation of this concept, but we don't want to miss it. If you read your book, they don't give you right away. They talk about the limits in word form only, but we want to get a good idea of what is the limit of the function is going to be. Okay, any questions so far? So this expression is kind of rounding, if you like the rounding that I did over here. Okay, so you round from the right or from the left, you lose or you may gain the numbers, but eventually you get to the a that's going to be. So these are going to be called one-sided, to the right, to the left. So this is not a negative sign. This negative means just less. This is not going to be a positive sign. This only means bigger than the direction. So right, from the left, two-sided, right and the left at the same time. Okay, any question? Now bring the function. For the function, the difficulty, function would have two variables. Remember, one of them is x, the other one is f of x or y. So when x do this type of estimation, so you drop this x value into the function. So the function would have the same, okay, same sort of estimation they're going to have. So what is going to be the, let's define the limit of the function very informally. It took mathematicians something like 50 years to arrive at the precise definition of a limit of the function. So if you take your, a couple of days, couple of weeks, or couple of months to understand it, that would be natural. But we try to help you to get to know it. So let's have a very informal definition of a limit. Bring a function. So suppose you have a function. Suppose a function f is defined. We need the domain. Is defined near a number A. Near a number A means your function is not supposed to define exactly at A because you don't care about the A. But it must be defined around the A. Around the A means this one. Look at this one. This is around the A. You don't care about the A. Anything to the right or anything to the left. Okay, so this is around means. So that's a definition of that, okay? Suppose a function f is defined near a number A and a number L is given such that the value of f of x, can be approximated, estimated, can be approximated by L whenever x, okay, whenever x approaches or getting closer and closer, approaches the number A. So this means you go to the right and the left of the A and you find the value of f of x. Value of the x, you see, would round up to the A. If the value of f of x, the output, also round up to the number like L, we say that the L is the limit of the function. That's it. If this is going to be the case, then we write limit of f of x when x goes to A is equal to L. That's it. And L is going to be, L is the limit of the function. Okay, limit of the function f at A, we call it, okay, when x approaches A. So that's a very informal one. Of course, in mathematics, we are going to make this one so precise. But this is the first definition of the limit of the function. It was done by a guy named Ampere. You know that Ampere is the guy that he just did, he was a physicist. You know that the Ampere, you know, this is the notation that we're going to use in physics for the intensity, I think. But he was the guy who just introduced this one first. Later on, it was Newton. It's like Newton that provided the definition, and it just go on in the history of mathematics, and eventually Cauchy, Agustin Cauchy, give us a nice definition of the limit of the function. Okay, so basically, if you want something easy to remember, therefore, we say that the limit of f of x when x goes to a is L, if and only if f of x is going to be approximately L whenever x is approximately a. That's a very informal and a nice interpretation of the limit of the function. Okay, we don't care about f of a. If you say f of a is the precise, exact value of the function f at a. We just estimate it. So you have to draw a table if you like. Get some numbers around the a, bigger than a, less than a. Then you find the f of x. Then you will see that when the x getting closer and closer to the a, then this f of x getting closer and closer to the number L. So in that case, you can claim that the limit of the function happened to be equal to the, equal to the L. Eventually, we are going to have some formulas, and we take care of it really. You get the theorem, and then you'll be very happy to use that theorem. But we are not going to rush that one. So be patient, get a couple of nice examples, then we give you a tool, a theorem, and then you just use that theorem happily, and you think that you did get the notion of the limits, okay? So let's give you one example, and just a classic example first that give you a better understanding of what I'm talking about. Okay, so let's get this example. We wanted to find this limit, you see, find the limit. Find the limit. So what's the limit? Limit of x squared minus x plus 1 when x goes to 2. That's it. You see, you want to estimate the value of x squared minus x plus 1 when x is getting closer and closer to the a, closer and closer to the 2. Okay, if you round up all the values of the x to the 2, what would happen to the x squared minus x plus 1? Okay, so what we're going to do, we are going to draw a table. X goes to 2, you know that x can be bigger than 2 or x can be less than 2. You have to check both of them to see what would happen to your function, and then you'll be done. Okay, so this is the way we do it. We need some numbers and a calculator. So this is the case. You see, draw a table. This is x, this is f of x. You want to around the 2. Remember what you're going to do. This is it. This is what you have to do. This is 2. You have to go from this direction and this direction to find out what is going to be the value of your function. So let's check one direction first. So what I'm going to do, I'm going to check this direction first. So I put the number 2. I make sure that I'm not going to pick the 2. Okay, take some numbers less than 2 and drop it into the function. Okay, some numbers less than 2. So you get the range. Suppose you want to pick the range from 1 to 2. You see, if you pick the 1 here, take 1 inside this function. What's going to be the result? If you put x equal to 1, you know, that's easy. 1 minus 1 would be 0, so that give 1. So that's 1. Okay, then I pick something like, I want to get close to the 2. okay, close to the true, I pick another number, something like 1.5. 1.5. Drop the 1.5 into this function. You have to use your calculator to get the, okay, to get the result. Okay. Number can be anything you like. Anything you like, but you must be close to 2. So you better pick something which is going to be close. Okay. So you can, there are infinitely many numbers less than 2. So since you are interested to see how you're going to run the DAB, so you better take a range between 1 and 2. But otherwise, yes, it's free. You can pick any number you like. So if you use your calculator and find this number, okay, I've already checked this one. So that give me 1.75. 1.75, okay? Pick another number. Remember, you want to get close to the 2. So close to the 2 with something like 1.9. If you put the 1.9 into this equation, okay, so you check your calculator, the result would be 2.71. Okay, 2.71. Then if you get a number, it's going to be closer to the 2. Okay, this is 1.9. So how about this one? Okay, how about 1 point, to be very much close, 9, okay, 9, 5. You see this number? If you run that, you get 2. So if you use your calculator and get this number, if you use your calculator, you can check it. So you arrive at the 2.985. Look at the top. You see input and the output. This is the situation that you have to the function. So your input are getting closer and closer to the 2 because 1.995 would be rounded up to the 2. But how about the bottom one? If you round up the value of the bottom one, what's going to be the result? Any suggestion? The numbers down the bottom? 2.985 would be rounded up to what? 3. Yes, very good. It's going to be 3. So as you can see, as we move on the top, if you pick the input to be closer and closer to the 2, which this number is very much closer, the bottom one, the value of the function, getting closer and closer to the, okay, closer and closer to the 3. You see, that would be to the 3. So what you did so far, you show that if x getting closer and closer to the 2 from the left, the value of the function getting closer and closer to the 3. So you can claim that the limit of the function when x getting closer and closer to the 3, but from the left, 3 negatives. I'm sorry, 2 negatives. That's 2. 2 negatives is equal to the 3. This is called the left limits. So the left limit would be 3. Any question? In your book, you have some assignments. The numbers on the top are given. So you have to follow those numbers. Otherwise, you can pick some numbers yourself. Okay? So we are not done because we did just one direction. So repeat it again. Pick some number from the other direction. Because you have to pick what would happen to the function when you're getting the values closer to the 2 from the right to the left. Okay? So get the second table. So what's going to be the second table? This is it. Again, we get the x and the f of x. So what you would like to do, you see, you consider the value less than 2. So how about the values bigger than 2? So you start with the 2. You make sure that you're not going to pick the 2. And you pick something bigger. You can pick any number you like. You see, if you pick a bigger number, you won't have any difficulty for the big numbers. Your difficulty would be the smaller number. So I'm going to get the range between 2 and 3. Okay, to find out what would happen to the value of the function. The minus sign means just the left, yes. This is not a negative sign, okay? Minus means x less than 2. Okay, plus means x bigger than 2. left, right from there. No, you're going to have it quite a lot. Okay, so let's make some numbers again. This is 2, something bigger than 2. Okay, so there you are, bigger but very close to 2. Okay? I pick something like, how about 2001? This number is bigger than 2, but it's very close. If you use your calculator, you drop it into this function. Okay, if you drop it here, the number would be 3.003. You can check it with your calculator. Okay, as you can see, this is going to be rounded up to the 3, but we need more evidence. So if you go away, if you pick another number very close, 005, for example, 005, and that gives you something like a 3 point, okay, I think it's 3.015, which is again very close. But you know, this would give you the result. If you pick the 3, that's a very bad case. If you put the 3, that gives you 7. So as you can see, again, as you're getting closer and closer to the 2, but from this direction, you see this is 2. So you're coming from the 2 from this direction. If you're getting closer and closer from the 2 from this direction, the value of the x would be rounded up to the 2. And the value of the y, you see the function, would be again getting closer and closer to the 3 in this case. So we can claim that the limit of the function, you see the limit of f of x, when x goes to 2, since you pick the bigger numbers, 2 positive. If you pick the 2 positive, so the result again is going to be equal to the 3. Okay, so what we did, there you are. Around the 2, the value is less than 2, the function getting closer and closer to the 3. Around the 2, x greater than 2, the value of the function getting closer to the 3. So this means the left and the right, you see, this means the left limit of f of x, when x goes to 2 negative, is going to be equal to the limit of f of x, when x goes to 2 positive, and is equal to 3. So you can claim that the limit of the function when x goes to 2 is equal to 3. So the result for this problem, so the limit is going to be equal to the 3. If you do these 2 estimations and the numbers are going to be different, if the numbers are going to be different, so in that case, you cannot have the limit, okay? So you estimate it from the right and the left, and both cases, these happen to be equal each other to get the numbers, okay? So that's going to be the case. If the limit does exist, this right and the left would be the same. But we give you some examples that this is not going to be the case. It's not the case that always you'll be able to find the limit of the function. So if the right and the left equal to each other, you get the limit. If not, in that case, the limit of the function does not exist. Okay, any question? So we want to get a good idea first, really, and then, of course, we are going to give you some theorems to be able to take care of it. This is just the beginning. These are not mathematically sounded, if you like. We can put them into the great version of the great formula that we are going to have. But in your case, we try to convince you with some examples and then just do the job. Then in a minute, you are going to have a theorem. You see, x squared minus x plus 1. What type of function is this one? X squared minus x plus 1. What type of function is this one? That we talked about the other night.
A polynomial.
Excellent, a polynomial. In a minute, we are going to give you a theorem. That theorem will tell you that if you have a polynomial, and if you want to find the limit of this function, the limit of the function and the value of the function are the same. So this means if you replace x by 2, so 2 squared would be 4. 4 and 1 would be 5. Minus 2 would be 3. And you're done. This is maybe do it in a minute, but we wanted to get the idea really. Just, give us your thought first, and then we give you a theorem. So we call it computing theorem. So we can compute the limits to get these numbers. It took mathematicians many years, at the beginning, when they talk about the limits, some people were confused that they substitute the 2. They say, oh, there you are. I substitute the 2, I get the 3. So what are you talking about? So the idea is going to be yes. For some functions, the limit and the value are the same, but it's not the case all the time. So the limit is not a substitution. It's an estimation that we are going to know, we are going to have. We're going to give you more examples in a minute. Okay, any question? So this is the idea like the rounding that you did. You see, in the case of the rounding, you have only one variable. Remember that number 1.5? You're just working, on the number line. You're working on the number line only. But in the case of the function, your difficulty is whatever, you see, x is a free agent in the domain. X comes first. So when x would be different, then f of x would have a target, if you like. So the target of the x would be 2. When x getting closer and closer to the 2, then f of x would hit its target, which is going to be 3. So it's a machine that one of them is depends on the other one in the case of the function. Yes, question?
Yes, I have a question. How come from the right, the limit is not 7? I'm confused with that part.
Why should be 7? This one, you mean?
Yeah, because like you see the other one.
No, you see, when
Mhm.
x getting closer and closer to the 2,
Oh, so we're going the other way. Oh,
this 7 is very far.
oh, I see.
That's why I was talking about. I said,
Yeah, sorry, I got confused.
yeah. No, don't worry. That's natural. You see, that was why I was talking about. When we say x getting closer to the 2, you may start from 10,000. But the 10,000, if you put the 10,000, you get a big number. But you must get some, you see, when the numbers are close, you have to check it, not when they are very big. This is very big, so that's why we ignore it, because you have to get closer and closer, okay? So this is where the limit would, would happen to get these numbers. And this is exactly what we do in everyday life. You see, we set up the target first, and then you have to do some activities to be able to get through it. So for example, your target in this course is what? To get an A. So how are we going to get the A? You see, A is this one. So how are we going to get the A? You have to manage the X to get the A. How are we going to manage it? You have to go through what? Your quizzes, okay? Your assignments. So for example, in order to get an A, you may need something like 400 points. So if you take your first quiz is 20 points. You are on target, but 20 is not close to 400. So you have to take the test one, make it to the 120. Then you have to take the test 2, quiz 2, quiz 3. As soon as you get to the end of the semester, you are going to be collecting enough points so your fx would get to the target. So this is exactly what we're going to do in everyday life. It's the other way around. You identify the limit first, then you manage it. You see, suppose you want to have your car, oil change for your car. As soon as you arrive in the shop, they give a piece of paper, they ask you to sign it. You sign it that the oil change for your car is going to be $200. So they have the target. They want to make the limit to be equal to the $200. So what they do, they start moving. You see these actions that we did. They check, they are going to tell you that, oh, we have to change your oil filter. Okay, oil filter. because they are getting closer and closer to the target. So they do such that at the end, they get $200. So that's exactly what we do in everyday life. So you set up the target first, then you go for it. You see, this is a situation that we're going to have with the function. Look at this one. This is what would happen. You see, this is your target on the x-axis, 2. Limit of the function would happen with the value of the function. So your target over here is 3. So what we did, we pick some numbers here. You see, we pick a number here. Then that gives us a number on the y-axis. We pick a number here that gives you a number around the 3. So as you go on far from the 2, these are going to be the number. But if you're getting closer and closer, you see these are going to be your numbers. So you go to the right and the left of the 2 here. Over here, you go up and down of the 3. You see? So as these getting closer and closer to the 2, the value of the function getting closer and closer to the 3. That's why you register 3 as the limit of your function. All the procedure that you do in everyday life is limit. It's the limit of the function because you set up the target and you make it. I can make these numbers as you like. You see, this your course is very wild one. The way we teach in calculus 1 is different. We exactly find out. This means you tell me how you want to estimate the value of the function. Okay, and I'm going to do it for you up to the 10th place, etc. But we are not going to spend time on that part. Any question on this one? So that's a good idea. Now, I'm going to give another example. Sometimes it would be nice if you don't have these numbers, but you have a graph of the function, okay? So you have a couple of them in your assignment. So it's nice to know it. I'm not going to give you any graphical one on the test because it's difficult for me to, to assign it, and we give you something different. So let's have the second example to give you an understanding. Then we go to the formulas. When you go to the formula, you find it so easy and nice to find the limits, but get to know it is very important. I'm a graduate of United Kingdom, so I know Bertrand Russell. You know that Bertrand Russell is English or a British mathematician and philosopher. He believed that this concept of the limit is the most important achievement of the human being, because they use it for for logic, philosophy, everywhere else. So such an important concept really. And there are quite a lot to talk about it, but we want to make it short. So this example, again, give you better understanding. Then I change this on into the algebra, and that would be your first question usually. So let's see. Without any number, we're checking your understanding. Okay, suppose the graph of the function is given to you only. Suppose the graph of the function y equal to the f of x, okay, is given. Let me finish the graph, then you can graph it for yourself. You see, this is it. Remember the piecewise defined function that we talked about the other night? This is the example, that sort of example. Okay, so I have one piece of the graph is this one. Suppose this point is going to be 1. Okay, then I have the other part of the graph. This is a solid point. This is the other part of the graph. Okay, I should give it a number that corresponds to this is equal to the, let's say 2. Okay, and the number that corresponds to this part is equal to, let's say 4. Okay, this is going to be 4, So we are going to ask you a couple of questions. Okay, this is it. So what we would like you to do is find each of the following. Find each of the following. Okay, so it's usually 4 questions. The first one, would like you to tell us what is the limit of f of x when x goes to 1 from the left, 1 negative. Okay, the next question is, would like you to find the limit of f of x when x goes to 1 from the right, 1 positive. Okay, and the third one, we want to know what's going to be the limit of f of x when x goes to 1. And the fourth one, we want to find out what is f of 1. See, this is a very important question to get these steps. Again, you have to do the estimation. You see the previous problem, you did have the f of x. So you just get those tables, remember? We do the same thing over here, but we use the graph. So just remind you how you read the value of the function from the graph. You see this going 1. Remember, if you pick a point here, and if you want to find the value of the function, you just get a vertical line that intersect the graph, then this is going to be the value of the function. Okay, so you have to, if you pick another point here, if you want to find the value of the function, this would be the value of the function. The value of the function on the y-axis, the value of the x on the x-axis. So let's see if we can estimate what's going to be the limit. So what do you want to do? First one. The first one, we want to know what's going to be the limit of f of x when x goes to 1 negative. 1 negative, remember, x less than 1. Pick some numbers. Less than 1 and estimate what is going to be the value of your function. You see, this is 1. Less than 1, you have to get from this direction. Okay, any number you like. So if I pick a number here, you see if I pick a number here, the value of the function is going to be this one, this number. Okay, so if I get closer, if I pick another number here, the value of the function, you have to draw the line, get the graph. So this is going to be the number. Okay, if I get closer, if I pick a number here, so what's going to be the value of the function would be close here. If I pick the number here, the value of the function would be here. So when you take x closer and closer to the one from the left, can you guess what's going to be the value of the function that would end up? Look at the y-axis that we're going to have to get these numbers. No, this is just a graph of a function. It's a random one. Any suggestion? You see, start x from the left. Start from the left, look at this one. I pick these numbers, it's way out. This number, this number, this number. As you're getting closer and closer to the 1, you see, you're getting closer and closer to this point here. And if you read this number, is already given to you. This number is 4. Yes, you're right, right. So this means the limit of the function when x getting closer to the 1 from the left is going to be 4 here. Any question? It's like the table that you did. You see, in the case of the table, you did have the numbers. In this case, we don't have the numbers, but we don't care. We just care to see. You see, when you get closer and closer to the 1, closer and closer to the 1, the value that you register on the y-axis is 4. Because you see, it's going to be bigger than 4, bigger than 4. If you start from here, it's going to be less than 4. Okay, so eventually you get to the 4. So this is a kind of a piecewise defined function. Remember, this portion is x less than 1. When x is less than 1, you see, look at your graph, down up to the partition point. Remember? The partition point, which is going to be 4 here. So this means the left limit of the function is equal to the 4, and we're done. Any question? So that was the table. This is going to be the graph. So what's that? How do you know when to stop going upward on the x-axis? And that's it. We know that. You see, this is going to be 1. We're getting closer and closer to the 1. So we pick the numbers to be closer and closer to the 1, and we see that we get to the 4. If you pick these numbers, you are on the top. You see, you are going to be around the 4. You see, this is 4. This is 4. So you have some numbers on the top, some numbers on the bottom. But when you get closer and closer to the 1, you register the 4. So that gives you the limit of the, okay, the left limits would be 4. Okay, the graph, it's going to be, you can graph it. No, 4 would be given to you, of course. Yeah, this would be a kind of on the, what is that, graphing table paper, those with the scales. So you will see the numbers. I don't have those scales. Okay, so that's going to be part 1. Let's see if we can guess the part 2. Part 2, the other way around, limit of f of x. When x goes to 1 positive, let's check. 1 positive, you have to come from this direction. So check some numbers, you see? If you pick the number here, what's going to be the y numbers? This is the y number. Okay, if you get closer and closer, what are you going to register on that?
Okay, I see.
Okay, what's that number?
It's 2.
It's 2. So in this case, this is going to be equal to 2. Okay, so if you're getting closer and closer to the 1 from the left, the values on the y-axis would be getting closer and closer to the,
Oh, so the line. I get
see,
it.
2 and 4. So what's your answer for part 3?
Would it mean that the limit does not exist?
Excellent, that's it. Does not exist because the right and the left are 2 different numbers. You see, from 2 different direction, you get 2 different numbers. We talk about it when you want to estimate, you should arrive at the same number, but we won't get the same number. So for part 3, we can argue that, say, since the limit of f of x goes to 1 negative, is not equal to the limit of f of x when x goes to 1 positive. Okay, that's what implies, or it follows. Okay, it follows that the limit of f of x goes to 1, does not exist. It's the way we write it down. Don't say no solution. You have to give us a reason. Okay, this is the reason. Because if they two happen to be the same, you say, since they are equal and equal to 5, whatever it is, therefore, the limit of the function would follow the same numbers. If they are going to be different, the limit does not exist. Any question? You will see in a minute, I'll give you the formula. I'll give you the function, but I didn't want to give you the function now because I would like to get the graph.
Can you read 3 again?
You see, since the limit of f of x goes to 1 negative, not equal to the limit of f of x goes to 1 positive, it follows that the limit of f of x goes to 1, does not exist. Okay. So, this is the expression that we're going to use for the does not exist. Okay, are you ready for the part 4? What is f of 1? You see, f of 1. This is not the limit. You pick exactly 1 and you go up to see where you are going to see the graph. You see f of 1, this is empty here. So f of 1 is not equal to 2 because this is a hole. You go on, this is a solid point. F of 1, the solid happened at 4. So f of 1 is equal to 4. That's it. F of 1 is equal to 4. We just wanted to see, you see, the value of the function is 4 at 1. But the limit of the function doesn't exist. So there are two different concepts. Most of the time, they may be the same. If we talk about it, if it's a polynomial, it's going to be the same, but this is not a polynomial. You see, this graph is not the graph of the polynomial because it's two pieces. The graph of the polynomial cannot be separated, if you like. Okay, so this means there is a connection between the limit and the value of the function, but they are quite different. So you have to check it, you have to find it to get what is going to be, what's going on. Okay, any question? So that gives you two different versions. Okay, this is kind of using graph picture, if you like, visually, and the other one just using estimated, table, if you like. But as you can see, this type of procedure, especially the first one, is not going to be easy to handle. This is mathematics. We set up a theorem first, okay? Then we are going to make it easier to go on. So what we are going to do, we are going to put the properties of the limit of the function in one great theorem. And we call it computing theorem. This means if you want to compute the limit of the function in this course, you are going to use this theorem. So that's going to be the idea of the computing theorem. Okay, are you ready to get this great theorem that makes things so easy for you? And these two examples was just to warm up, just to understand it really. That's very important to understand the notion of the limit of the function. Okay, so let's see how we are going to make things easy. I'm going to call this one computing theorem. Let's see what is going to be. Computing theorem. So I just remind you that you can apply this one. One can, apply. One can apply the following theorem. Apply the following theorem, to find the limit. In this course, you're just using this theorem, find the limit. The limit of a function. I'll give you other interpretation of the limit later on again, the history. Okay, so what's that great theorem? There you are, theorem. Let's see what this theorem is about. Just one word, one expression. You see, we have, when we have functions, we have operation with the functions, fundamental operations with the function. What's that? Adding, subtracting, multiplying, dividing, taking the square root, cube root, etc. So this theorem will tell you that the notion of the limit and these fundamental operations commute. What does it mean? This means if you want to find the limit of the sum of two functions, the limit of the sum of two functions is the sum of their limits. And you find the limit of the first one, you add it to the second one. We call it addition rule. If you want to find the limit of a difference of two functions, you find the limit of the function, the first one minus the second one. So this commute. If you want to find the limit of the product of two functions, is the product of the limits. You find the limit of the first one times the second one. If you want to find the limit of a quotient of two functions, commute, quotient of the limits. You find the limit of the first one, you divide it by the second one. If you want to find the limit of the square root function, you take the limit inside the square root, okay? So this is basically the notion of this theorem. And that would have one conclusion that we're going to use for the computing the limit. Okay, so I'm going to write it down. There you are. Suppose, of course, the limit of those functions does exist. Suppose we know that the limit of f of x when x goes to a is given to, let's call it L, and the limit of g of x, okay, when x goes to a, we call this one m. Okay, limit of f of x, x goes to a is L, and the limit of g of x, x goes to a is m. Then we are going to have the following. The first one, addition. If you want to find the limit of f of x plus g of x, okay, when x goes to a, limit of the first one plus the limit of the second one. It's like distribution. So that give you what? That give you limit of the first one, limit of f of x, x goes to a, plus the limit of g of x, x goes to b, x goes to a. So the first one is L, the second one is m, done. Okay, makes things so easy for us. It's the same for subtraction. So if you have a difference, it's going to be different. That's it. Okay, limit of the sum, sum of the limits, limit of the difference, difference of the limits. That's the first one. Question? What's the second one? Second one, product. First, if you multiply a function by a number, what is the limit of the 5 times the function? Of course, it's the 5 times the limit of the function. You see, commute. So get a number. If k is a number, 2, 3, 4, 5, 6, then the limit of k times f of x when x goes to a, the limit of k times f of x, s goes to a, is going to be the same as k times the limit of f of x, x goes to a. Okay, the limit of the k times the function is k times its limit. Okay, which is equal to the k times L. So if you have a coefficient, 2 times, 5 times, keep it. Find the limit first. If the limit of the function is 2, 2 times 5 would be 10. So we are not going to bothering. But they are going to be used, in for some other purposes. Okay, so this is a multiplication of a function by a number. Next, the actual multiplication. Okay, so the next one. How about the limit of the f of x times g of x? Okay, limit of the product when x goes to a is the limit of the first one times it by the limit of the second one. Okay, limit of the first one is L, and the limit of the second one is M. It's going to be L times M. Okay, limit of the product of the function, you get the limit of course, this limit must exist, and we already assume that we do have it. Okay, so must make sure that you have the limit of those parts. Then we get to the product L times M. Okay, the product, the sum, the difference, multiplied by a number. What next? The division, quotient. The limit of quotient, f of x over g of x when x goes to a. If you want the limit of the quotient, you go up and down. You find the limit. You see it's going to be equal to up and down. So that's going to be limit of f of x. X goes to a. And this is going to be limit of g of x. X goes to a. So the top would be L, the bottom one would be M. So the limit of a quotient of two functions is the quotient of their limits. Give us the result. And there is one condition over here. What's that condition? Any suggestion? One of these numbers cannot be zero. Which one is it?
The limit of g of x.
That's it, very good, M. So M cannot be zero. So we just say that, oh, we know that M cannot be zero. You know that you cannot divide by zero. So we have to assume that the M is not equal to the zero. When M is not equal to the zero, automatically G of X won't be zero too. So that's going to be the one. How does one know what? It's a limit of the top divided by the limit of the bottom. You see, this is it. Limit of the top, limit of the bottom. Limit of the top is given to you L, limit of the bottom one is given to you M. You see, you do have these limits at the beginning. You have the limit of the theorem will tell you that if you want to find the limit of the quotient, you find the limit of the top and the bottom. If you have it, the top is L, the bottom one is M. So L over M. Okay, any question? So we did take care of all the operations, but how about the other operation like, how about taking, if you have a radical, okay, how about if you want to find the limit of the n root of f of x when x goes to a. You see, that's what. Again, what you can do is you take the limit inside. You see, if you stop outside the radical, you can't do anything about it. So you have to take the limit inside. So it's going to be n root, okay, of the limit of f of x, x goes to a. Then, of course, this limit is already given to you, it's equal to the L. So that would be n root of L. See, make things so easy. So it's going to be a square root, cube root, fifth root, sixth root, it doesn't matter. Whatever it is, we are ready for it. Okay, that's a number 5. Any question? Number 6, we already talked about it. If we have to take it into the one-sided, we know that this theorem, we already used this one. Number 6. Number 6, the limit of f of x when x goes to a is equal to the L. Remember, if and only if. The right and the left limits happen to be the same. The limit of f of x, okay, x goes to a negative, is equal to the limit of f of x, x goes to a positive, and of course it's equal to that. We mostly use it, when we want to reject it. We talk about it. If the limits are different, then the limit does not exist. If it does exist, the right and the left must be equal to each other. Any question? No. This number 7 is the one that you're going to use. So it's going to be number 7. This is your tool. How about if we have a polynomial? Okay. So if P of x is a polynomial. A polynomial function. Remember, the polynomial function is just a combination of powers of x. Okay, like 3x squared plus 2x minus 1. You see, if you're given a polynomial, since it's a combination of monomials or powers of x, so what you can do, you can use this theorem. You see this one? So you take the limit into each term. It's going to be limit of the, for example, x cubed plus limit of the x squared, limit of the 5x. Then what you can do is the powers of the x would be just the product. So we change them into the product. So eventually what you arrive at is that the limit of the polynomial is the same as the value of the polynomial at that numbers. So if you have a polynomial and you want to find the limit of this polynomial when x goes to a, simply it's going to be p of a. We just substitute. Only if it is a polynomial. Remember the polynomial, like, x cubed plus 5x squared minus 7x plus 1, that's a polynomial. Okay, that would be the polynomial. So if you get a polynomial, according to everything I talk about over here, you just, when you replace, you see, when you just apply this theorem, you end up with something like limit of x. X goes to 2, which is 2. So if you have a polynomial, so you can use this fact and nicely substitute to get the result. If you have anything else, you have to use the other part of the, okay, this theorem. So that's a computing theorem. I give you a break. We come back and we are going to do it. You are going to get something like 12 different problems, at least, that resulted from this theorem. And those 12 is the one that we are going to work with during this course. Okay, it's almost, what's the number? It's 8:30, 10 minutes. I come back and we start working on those, okay, those exercises. And you'll be able then to do all the problems of 1.5. See you in 10 minutes. Okay, so let's get some example to see how we're going to apply this theorem. Okay, any question? So let's give examples to see how we're going to apply it. Okay. And this is the way we're going to operate and the way you're going to write it down on the, okay, on the test, on the quiz. Okay, there you are. Example, we wanted to find each limit. Okay, there you are, find each limit. Start with the first one, okay? This is it, number 1. You want to find the limit of 5x cubed minus 4x plus 1. When x goes to -1. You see, that's it. What type of function is this one? 5x cubed minus 4x plus 1.
Polynomial.
Polynomial.
That's it. We talk about it. If you have a polynomials and you want to find the limit of the function, you see, the limit of the function, the same, the value of the function is the same. Just substitute. Okay, so this is going to be the solution. I rewrite it. The limit of the 5x cubed minus 4x plus 1. X goes to -1. Substitute. 5 times the -1 cubed minus 4 times the -1 plus 1. -1 cubed is going to be -1 times 5 would be -5. Okay, that gives a +4 and 1. So you add them together, the result is going to be 0. So the limit of the function is 0 and you're done. Any question? So this is, we're going to write it down, polynomial, and just substitute the result. Don't try to do some crazy operations. Okay, some people, they they use that theorem, they separate this one, write it down as a limit of the 5x cubed minus limit of the 4x plus the limit of the 1. Then they separate that one again. Don't waste your time. This is a polynomial. The limit of the polynomial is just the value of the function. You substitute, you get the result. One line only. Any question? That's case 1. Okay. What is going to be case, okay? What is going to be case 2 that we are going to be interested in? Okay, just check to see if I give you everything in order. Okay, the next one. The next one, you would like to find the limit of, okay, the limit of the, let's say, cube root of the 7x. Okay, that's going to be cube root of, we get the 7x. Okay, so that gives you 7x to get the something nice, plus 6. Okay, and this is going to be when x goes to 3. This is a radical function. We talk about it. If you want to find the limit of the radical, you go inside the radical. Okay, so the solution is going to be, you want to find the limit of the cube root of the 7x plus 6 when x goes to 3. You go inside, it's going to be cube root of the limit of the 7x plus 6 when x goes to 3. What type of function is 7x plus 6?
Is that also a polynomial?
Yes, it's a polynomial. And you know that for the limit of the polynomial, we substitute. Cube root of 7 times 3 plus 6. 7 times 3, 21. 21 and 6, 27. Cube root of 27 is equal to 3. Because 3 times 3 is 9, and 9 times 3 is 27. So the limit of the function is equal to 3. Any question? Again, you see, I use those theorems one by one to get these, okay, to get this number. question? So let's see what's going to be the next group. The next group are going to be interesting. Okay, we get the number 3. What's the number 3? We would like to find the limit of this function. Limit of, okay, on the top, you get something like 7x squared. Okay, we get the 7x squared, and this is a plus 8x plus 1 over 2x plus 3 when x goes to a -1. You see it's a quotient function. You know that the limit of the quotient function would be the limit of the top divided by the limit of the bottom. What is the top and the bottom? What type of functions are the top and the bottom?
Polynomials.
Polynomials. And you know that for the polynomial, you just do the substitution. Okay, so directly we substitute. So we want to find the limit of 7x squared plus 8x plus 1 divided by 2x plus 3. When x goes to -1, substitute. Is going to be equal to, on the top, make sure you use parentheses, 7 times -1 squared plus 8 times a -1 plus 1. And the bottom one would be 2 times -1 plus 3. Okay, so that would be equal to the top -1 squared is a positive 1 times 7 would be 7. Okay, that gives you -8 plus 1. The bottom one is going to be -2 plus 3. Any question? Now the top would be 0. The bottom one would be 1. So what is 0 divided by 1? 0 divided by 1?
1.
0. 0 divided by any number is 0. So this would be 0. Okay, so you may try, to find the limit of the quotient, and you may arrive 0 on the top only. If you get a 0 on the top only, in that case, the limit of the function is 0. You're not done. Some people on the test, you see they leave it as is. You're not done because you have to do the division, okay? 0. When it's a 0, it's already 0. What do you want to do? You want to divide it by something, it would be 0 again. So the limit of the function would be 0. Question? Now, the next one is interesting. Number 4. And you have all of them from now on. Any on your test, the reviews, they are going to be all over the places. Just pay attention. So let's see what's special about this one. Limit of, let's say x goes to 1. X goes to 1, the top is going to be 5x squared, okay, minus 4x minus 1. And that's the top. And the bottom one is going to be x squared plus 5x, okay, minus 6. You want to find this limit. Try to see if you can do it. You know that it's a limit of a quotient, it's a limit of the polynomials, ratio of the polynomials, then you do the substitution. Just substitute to see what's going to be the result. Substitute, simplify. What do you have? Yes, let's see. You say 0, 0, 0, 0. No, you won't get 0. You see, if
Is
you
it error?
but which one? Yeah, we get 0 over 0. Okay, so that's going to be a difficulty. Let's see what's going to be difficulty. So I'm going to rewrite it. It's going to be the limit of, it's a 5x squared minus 4x minus 1. And this is going to be x squared plus 5x minus 6 when x goes to 1. So if you substitute, so the top would be 5 minus 4 minus 1. And the bottom one would be 1 plus 5 minus 6. So that would be 0, 0. You see, that's going to be the 1. Now let's see what does it mean, 0, 0 over here. Okay, this is going to be 1. Okay. Now, it's not undefined. You see, in your previous courses, when they get 0, 0, they say it's undefined. This type of example shouldn't be tried in any other courses than calculus, because this is in calculus that eventually you get to this type of ideas. You see the 0, 0, we are going to call it undeterminate form. What does it mean? This means that this type of situation would have a solution, but the solutions are going to be different. In one case, you may get 1. In one case, we get 7. So we are not going to be able to tell us or to tell you what is going to be the result right away. But when we get the 0, 0 in calculus, that gives you a message. So what's the message? Let's see why you did get 0, 0. You get the 0, 0 because you put x equal to 1 on the top. You know that if you put x equal to the 1 on the top, you get the 0. This means x equal to 1 is a solution of this equation, 5x squared minus 4x minus 1. If you let it equal to the 0, one of the solution would be 1. So how you find the solution of an equation? You factor it, remember? The reason that you get 0 is that x minus 1 is a factor of the top. At the same time, you get the bottom equal to the 0. The reason that you get the bottom equal to the 0 is, okay, x minus 1 is also a factor on the denominator. So when we get this 0, 0 in calculus, or in these cases, this means the top and the bottom have a common factor. That's why we get the 0, 0. You have to find that common factor, eliminate it. When you eliminate it, you are not going to have a 0, 0. You just substitute and then you get your result. This is how we're going to handle these type of problems, okay? So we call it undeterminate form, okay? Undeterminate form, and there is a message. The message is the top and the bottom would have a common factor. What is that common factor? You see, this is x goes to 1. You also pull x to 1 to the other side, x minus 1. So this means, this is just for your information, x minus 1 is going to be a common factor. Common factor. If x goes to negative 1, x plus 1 would be common factor. So that will help you to factor the top and the bottom. So what we're going to do, we're going to factor the top and the bottom. So what's going to be the result? So the top would be the limit of x goes to 1. You see, you already got the common factor. So you know that 1x minus 1 is on the top. 1x minus 1 is on the bottom. So you have to find the other factors. See? Which is very easy to find. Because you see, this is a negative 6. How are we going to get the negative 6? It's going to be negative. This is x. Because this is x squared. So you have to create the negative 6. You already got the negative 1. Negative 1 times what would be negative 6? Give us a number. Negative 1 times what number is going to be negative 6?
6.
6, possible negative?
Positive.
Positive 6. That's it. Okay. So we already got the negative 1. Okay. is going to be yes, a -1, that's a +6. The top is a 5x squared. So we got the x. So we need the 5x here. Now the numbers, you need a -1. Okay, you already got the -1. So -1 times what would be -1 again?
+1.
+1. There you are. You see, I know that, from your algebra, you use grouping those type of ideas to factor it. But that will help us because we know one of the factor. So pull out that one factor, x minus 1, x minus 1, quickly find the other ones. Okay, over here, this is x minus 1, this is x squared, so x would be x squared. We have a -1, we want to get the -6, so -1 times +6 would be -6. The top one, this is x, you have the 5x squared, so it's going to be the 5x, okay? 5x squared, and the -1 times the +1 would be -1. That's it, we have the common factor, we are going to eliminate it. Elimination means dividing, you see? So that would be 1, 1. So this would be the limit of 5x plus 1 over x plus 6. When x goes to 1, we reduce it if you like. Now substitute. You substitute x equal to the 1, so that gives you 5 plus 1, 1 plus 6. So that gives you 6, 7. The final answer. It's very common practice in calculus. And you are going to see this type of problems again when we get to there, okay? When we get to the next section. So identify the common factor and eliminate it. Your writing is important. Look at my writing. As long as there is an x, you have to keep the limit. When you substitute, you're done with the limits. Now this is very crucial. Why? Because there is no canceling in mathematics. You divide. You see, divide top and the bottom x minus 1. When you divide, you must make sure that the x minus 1 is not equal to the 0. So how are you going to guarantee that x minus 1 is not equal to 0? The limit. Remember, x goes to 1 means x is not equal to 1. Remember? You estimated x is not equal to 1. When x is not equal to 1, x minus 1 is not 0, so we can eliminate it. On the test, most of you, this is the way you write it down. They write this one, okay, without the limits. If you do this one, you take some points out because I put the question mark for you. I put the question mark is, how do you know that x minus 1 is not equal to the 0? Okay, but when there is a limit, that's it. X goes to 1 means x is not equal to 1. Okay, x is not equal to 1, so we can simplify. So make sure that don't lose some points on this, on this problem. And you know the difference. Okay, we find out x minus 1 is a common factor because when you put x equal to 1, we get the 0 here. You see, this is it. If you let this equal to the 0, the first factor 0, that gives x equal to 1. So if x goes to 1, the common factor is x minus 1. If x goes to -2, would be x plus 2. Okay, so this is the way quickly you have to identify that common factor to be able to to get there, to get through it, to get these numbers. Any question?
So where did the 4x and the 5x go
It's
when you were
inside. No,
when you were
it's in-
factoring?
It's inside. If you multiply it, you would see it. You see, if you multiply, you know that you FOIL it and you combine the like terms. If you FOIL it, so that give you x times 1 would be a positive x, okay? 5x times -1 would be -5x. So the -5x and x would be -4x.
Okay.
But automatically, if you arrange these, okay, those terms, automatically it works, okay? So you don't have to check it. So you have to check these constant that you get. You see the -1 and the -6. So the rest is coming and we don't have to check it. Any question? So 0, 0. message. What's the message? There is a common factor. What is the common factor? If x goes to a, the common factor is x minus a. That's it. You move it to the other side, you get the common factor, you simplify it, and then you're done. Okay, question? Some people, you see for this one, there is something not in calculus 1, in calculus 2. There is something that by a French mathematician, L'Hopital. We call it L'Hopital rule. We can take care of this type of problems. But remember that, you know, you are going to learn it in calculus 2 at the end of the calculus. You cannot use that right at the beginning. They say, oh, I take the derivative. What do you mean by derivative? This is section 1, okay? So if you know it, if you see it somewhere, then you'll be questioned because we don't know those type of ideas, okay? Easy to get these numbers. Okay, that's case 1 for the 0, 0. We have another one. Any question? You will see this is just a foundation of whatever we are going to do in the next chapter. So that's a 0, 0. Now, there is another case for the 0, 0. Look at the term. We have a polynomial, okay? The top and the bottom. So we get a case that it is not going to be a polynomial. And that's, okay, there is going to be a story about this that I would like to tell you that when this type of idea was done by, okay, first by Newton, these type of ideas, and the people didn't have a good understanding of x goes to 1 or if they substitute. There is a, you know that Isaac Newton is English mathematician. There is another English mathematician, his name is Bishop Berkeley. He was a bishop, but at the same time, he was, you know, interested in mathematics. So he wrote to Newton and he argued that your proof over here is providing a paradox, if you like. And he claimed that exactly what I talk about it. He said that when you want to simplify, you are going to assuming that x is not equal to 1, because in that case, you can simplify it. But over here, he said, when you simplify it, then you substitute x equal to 1 to get your limits. So he said, this doesn't make sense. And he just argued with Newton that, you know, it's history. That when you come to the church on Sunday, you ask me to prove everything, you argue, but this is your proofs. In that time, it was just the beginning of a notion of the limits, and Newton, you know, replied that, yes, I know that there are some difficulties, but this idea is useful. Let's use it. But now we know it. You see, it's not a substitution, it's estimation. But then we proved that since they are polynomials, the estimation and substitution happen to be the same. So nothing wrong with this type of arguments. Okay, there are quite a lot. As I told you, it took mathematicians many years to convince each other. That's going to be one. Okay, so what's the question? I don't understand your question. Correct that significance. They share a common factor that needs to be eliminated. No, 1, 1, no. 1, 1 is equal to 1. There is a nothing. 0, 0 is the one that you'll be in trouble. Okay? 0, 0 is the troubling. No, if you get 1, 1 is equal to 1. Okay, just 0, 0. Okay, let's give you, make sure you get the other one too. We have kind of 3 cases. So this next case is again very useful. You're going to see it at least 3 more times. So let's start with something original. This is originally was given by Newton, and you will see it in the next section. Okay, let's have x minus 4 here, and radical x minus 2 over there, and x goes to 4. You see, it's a very popular one. If you substitute, automatically you get 0, 0 again. See the solution? So we want to find the limit of the radical x minus 2 over x minus 4 when x goes to 4. We substitute. We hope to be able to do it. Radical 4 minus 2. Okay, that's going to be 4 minus 4. So that gives you 2 minus 2, and this is going to be 0, 0, 0. Question mark. Message. What's the message for this one? Message. The message is the top and the bottom would have a common factor. The reason that you get the 0, 0 is that you get a common factor. What is that common factor now? Yes,
X minus 4.
excellent. X goes to 4. The reason that you get it because x minus 4 is a common factor. You see, x minus 4 is a common factor.
Oh no, it's 4.
You see, because you put the x equal to 4 to get the 0. So how did you get x equal to 4? It was x minus 4, you let it equal to the 0 to get x equal to 4. So that's going to be the idea. Now we have to go back, find it, eliminate it. You see the bottom one, you already x minus 4. So you have to create x minus 4 on the top. It's not a polynomial to factor it. Okay, so how we're going to do it? The way we are going to do it, remember in algebra, you did have something, we call it rationalizing. Rationalizing the denominator or numerators. So you have to remove this radical to get x minus 4. So to rationalize, you multiply the top and the bottom by the conjugate of the radical expressions. What does it mean? Radical x minus 2, the conjugate would be radical x plus 2. So you multiply the top and the bottom by radical x plus 2, automatically you remove the radical and you get x minus 4. So that is going to be the procedure for the type 2 of the 0, 0. Okay, we get the 0, 0. So we start it over. You see, this is how we're going to do it. This is going to be the limit of the radical x minus 2, x minus 4. X goes to 4. So it's going to be equal to the limit of x goes to 4. The top and the bottom by conjugate of the top. You see, this is the top. Radical x minus 2. You multiply by its conjugate. The conjugate, we just change the middle sign. Radical x plus 2. You do the same thing to the bottom. X minus 4, okay, times it by radical x plus 2 again. Any question? You multiply the top and the bottom by the conjugate of the top. Now you should be able to create x minus 4 on the top. You are not going to touch the bottom one because you have the common factor you are looking for. So the top, you see that's a special product in algebra. Remember, a minus b times a plus b would be a squared minus b squared. So it's going to be radical x squared minus 2 squared. So we continue. It's going to be limit of x goes to 4. The top would be radical x squared. Okay, minus 2 squared. And the bottom one would be x minus 4 times it by radical x plus 2. Any question? The top is just the FOIL method, the special one. Radical x squared would be x 2 squared 4. You see, x minus 4 on the top. The bottom one as is, x minus 4 times, okay, times the radical x plus 2. Now we have the common factor that we are looking for. You see, this is going to be the common factor. X goes to 4, eliminate the common factor. You divide by x minus 4, that give you 1. And the x minus 4, this is 1. So we are going to get equal to the limit of, the top would be 1. The bottom one would be radical x plus 2. Radical x plus 2, x goes to 4. Any question? So this is the way automatically you eliminate that common. You create the common factor this time. You create it on the top and then you just eliminate it. Substitute, you get your result. So if you substitute, that give you 1 over radical 4 plus 2. Radical 4 would be 2. 2 plus 2, a quarter. The final answer. You don't have to, but I rewrite it. Radical x minus 2 over x minus 4. X goes to 4 is equal to a quarter. Very popular procedure again for finding the limit of this type of function. We have something we call it derivative of the function in the next chapter. You just find the derivative of radical x when x equal to 4. So we are going to get back to these type of problems again. Okay, so 2 cases. There are 4 cases, but we just stay with 2 cases in your case. That you are going to have the 0, 0. So if you may get a 0, 0, the top and the bottom are polynomials, so you factor it. And you know one factor, so easily be able to find the second factor. And the other part is if you get the radical expressions, then you have to multiply the top and the bottom by the conjugate of the radical expressions. We call them rationalizing the denominator or numerators, doesn't matter. So automatically, you see, you are not going to touch, you leave this one as is, just focus on the top, is the square of the first minus the square of the second one. So that gives you x minus 4. You have the x minus 4 nicely eliminated, and then do the substitution to get the final answer. Okay, the theorem, you see, I just used the theorem here, or a kind of a special FOIL method. You see the FOIL method that I apply. This is it, a minus b times a plus b is equal to the a squared minus b squared. That's exactly what I did when I multiply these two together, okay? It's going to be a square of the first one, radical x squared, minus the square of the second one, which is going to be 2 squared, you see? A minus b times a plus b. A squared minus b squared. The radical x squared would be x, and the 2 squared would be 4 to get these numbers done. Okay, any question? So that would give us the case 5. Let's see if we can get the 6th one as well, because the 6 is important. Okay, remember that example that I gave you? This was the one. Just find the right and the left limits. Now I'll give you the real one. I'll give you the function. This is again a very popular case. I'm going to question you on all of them, so just make sure you know it. I post the practice quiz number 1, take home quiz number 1, so you see these problems, and we go over it, okay? And we need to practice more for this section. Now, this is the next case. Suppose a piecewise defined function is given to you. Suppose f of x is equal to f of x is equal to the x squared minus 3x when x is less than 2. And is equal to the 5x plus 1 when x is greater than or equal to 2. A piecewise defined function partition around the 2. They ask you to do those 4 questions that we did. Find each of the following. Each of the following. Okay, the first one. Limit of f of x when x goes to negative. The second part. Limit of f of x when x goes to positive. The third one. Limit of f of x when x goes to 2. We're just focusing on that partition point. And the fourth part, f of 2. You see, that's a very popular case, and you have a number of them in your book. These are the so-called one-sided limit, right, left, that we talk about it. We did those one with the graph. Now we do the actual one. Are you ready? You see, these type of limits are going to be around the partition point 2. When x is less than 2, this is the function. When x is bigger than 2, this is the function. So for each case, you have to decide which part are you going to use. Are you going to use the first part or the second part? And this is how we're going to do it. Solution. You see the first one. You want to find the limit of f of x when x goes to 2 negative. Remember 2 negative? 2 negative means from the left. So x goes to 2 negative. What does it mean? I'm going to explain it for you. What does it mean? Any suggestion? X goes to 2 negative. Means x approaches 2 from which direction? Right or left?
The left.
Left. Yes, it's going to be left. When it's a left, you know that when it's a left, this means x is less than 2. Okay? When x is less than 2, what's your function? See your function? Your function is the first part. So this is how you talk to yourself. I write it down, so that you know what we are talking about. So we say, oh, x goes to 2 negative, means x is less than 2. When x is less than 2, my function is x squared minus 3x. So I have to use this one. Okay, so you have to find the limit of x squared minus 3x when x goes to 2 negative. From now on, it's just a substitution. Because the number is 2, you know that this is just a direction. So this means it's going to be 2 squared minus 3 times 2. 2 squared is 4 minus 6 negative 2. This is the left limit. Any question? So you have to decide which part are going to use. The first part or the second one. Just look at this one. X goes to 2 negative, you're going to the 2 from the left. So x below the 2, if you like, you see. X is less than 2. When x is less than 2, your function is the first part. The function is going to be a polynomial. You just substitute to get your numbers. So the left limit is negative 2. Okay, let's see what's going to be the right limit. Limit of f of x. X goes to 2 positive this time. Again, these are just for your information. 2 positive means from the right. From the right means what? X is greater than 2. So when x is greater than 2, this is your function now. So you have to use the, on the test, just use it right away, but just explain it. So you have to find the limit of 5x plus 1 when x goes to 2 positive. This positive and negative is just a direction, you just substitute. So it's going to be 5 times 2 plus 1. 10 plus 1, which is 11. You see? The left and the right limits. Any question? What's the answer to this one now? Limit of f of x when x goes to 2. You see the 2 is the partition point. So you have to check the right and the left limit that you have. You see, the left limit is negative 2. The right limit is 11. So what does it mean?
It's neither.
It does not exist
Does
because
not
they're
exist. That's it. Because the right and the left limits are
not the same.
different. Yes. And this is the way you're going to explain it. You say, oh, the limit of f of x when x goes to 2 negative is not equal to the limit of f of x when x goes to 2 positive. So that would imply the limit of f of x when x goes to 2 does not exist. That's it. If they are going to be the same number, that same number is going to be your limits. You see, for the partition point, you can't do it right away. You have to do the one-sided one. In calculus, whatever you want to do for that partition point must be one-sided, right, left. Any concept, you are going to have a couple of more concepts again, it's going to be the same thing. So the limit does not exist. Question? Now, the last part. How about f of 2? You see, that's the exact value. X equal to 2. You go back to see where you can put x equal to 2. The first or the second part?
The second.
The second. If this second is also coming strict without any equality sign, f of 2 is undefined. But you have it with the second one, so use the second one to find it. So it's going to be 5 times 2 plus 1. 10 plus 1, 11. So that's going to be the case. It's a very popular problem in calculus, okay? And there are two other possibilities of these type of problems. The possibility that these limits are going to be the same. If they are going to be the same number is your limit. And the case that you cannot put x equal to 2, in that case, f of 2 would be undefined. And you will see them, when you get to those exercises that we have. And that's it. We did a number of good ones. There are a couple of more to understand it. So we talk about that one. Okay, that's it on on Thursday. On Thursday, and we are going to wait. This section is very important, so we are not going to rush. Just make sure you understand everything. Then we go out of this this section. So have a look at these examples, and if you like, you can look at the 1.5. But I'll post the practice one, take on one. So we got to practice on these type of ideas, and then we continue. It's a foundation.
Professor?
Yes.
So on the homework, you were saying to do 7 questions. Are you saying 7